now we're going to move to our second speaker of the day. Professor Junyi Geng is an assistant professor in the Department of Aerospace Engineering at Pennsylvania State University. She was a postdoc fellow with the Robotics Institute at Carnegie Mellon University, where she was a member of the Air Lab working on aero manipulation and eVTOL. Before that, she was a postdoc research associate of the Coordinated Science Lab at the University of Illinois Urbana-Champaign, working on robotic manipulation for high-precision assembly. She received her PhD and master's degree in aerospace engineering with a minor in electrical engineering from the Penn State, and holds a BS degree in aircraft design and engineering from Nanjing University of Aeronautics and Astronautics. She's enthusiastic about robotics and unmanned aero systems, as most of us here at the Maryland Robotics Center. She is also interested in computer vision optimization and machine learning, is a remote pilot for UAS systems, and loves flying drones and building robots. And so with that, we're very excited to cede the floor to Professor Geng.
All right, thanks, Yanxi. Let me share my screen. Okay. Everybody see my screen? Okay, good. Yep. Hello, everyone. It's very nice to be here, and thanks for the invitation of the MRC. I'm very glad to present some of my related work interacting with the environment for autonomous aerial manipulation. Yeah, today there are many hazardous tasks that have high altitude that are still manually performed, such as the human climbing to the high tower to changing a light bulb, like painting a gigantic pipe, or even do the bridge repair, or the wind turbines maintenance, or even carry a super large payload, but just building an even large helicopter. But when performing this, when climbing to the structure is expensive, inefficient, and hazardous to human life. For example, when performing the routine wind turbine maintenance and repair, so 100 people dies on average, every trillion watt-hour, just by falling every year, not to mention the death caused by electric shock. So for the bridge repair, just getting the super truck in place requires an incredible amount of logistics. You can imagine the traffic must be controlled on both sides of the bridge to provide room, and the traffic must be limited. So the rapid growth of autonomous unmanned air vehicles, or UAV, has the potential to provide a safer and more efficient solution due to the ability to fly to the high altitude. But although the use of UAV has grown very rapidly, so most of today's vehicles still focus on the passive tasks, such as the drone used to do the high voltage power line inspection, and this is the Skydio drone tracing a human body, and the monitoring or the remote sensing. So we're asking, why don't we leverage the advantage of the high altitude of the drone to really let them to help humans do something beyond just the passive tasks? So aerial manipulation is intended to perform such kind of manipulation tasks, such as grasping, transporting, positioning, assembly, and disassembly of mechanical parts, etc., which can assist human in performing tasks at high altitude or in a hazardous situation. But so far, the aerial manipulation has mainly explored in the controlled lab settings, such as drawing letters, pushing a door, and really not widely used in practice. So this is because the unique challenge of this problem. Let's take a look at that. So unlike the robot arm usually mount on the desks, so this aerial manipulation problem, you first need to have a floating body, which is the drone, float in the air to maintain its own motion. So then it performs the manipulation tasks. At the same time, the manipulation performance will, on the other hand, affect your self-motion control quality. So this coupling nature really makes this problem challenging. So additional challenge come from some of the perception uncertainty, such as when you bring all the robot outdoors, like the localization challenge, the localization uncertainty, or other kind of uncertainty add additional challenge to this problem. And the final goal is to achieve a precise contact control to maintain the manipulation performance. So my previous work tried to address the two key points, which is the perception and manipulation of this aerial manipulation application. So today, I would like to share some of my previous work on some of the autonomous manipulation application I did for the past several years. So the first one I'd like to share is the aerial transportation project, which is a very early work during my PhD. We call it a multi-lift or the aerial robot cooperative transportation. So the idea is to use a fleet of smaller aerial robot to coordinately carry a single slung load so that the total payload capacity is increased without the need to building a super large or heavy vehicle. So this research consists of 3 parts, which covers control, estimation, and trajectory planning. So we developed a comprehensive hierarchical load leading control strategy. In this strategy, the payload actually is the team leader. We attach the electronics on the payload so that the payload can sense itself and command the whole fleet as a team leader. So at each timestamp, based on some desired trajectory, the payload will compute the net force and moment that should be acting on itself to steer it from the current state to the desired state. Then the cable force on each individual cable will be computed based on the desired cable force. Then each of the desired rotorcraft states will be computed based on the cable tension and the desired payload states. So we can see the key part is for the cable tension computation. So it ended up with a underdetermined system with infinite number of solutions. So I formulate this problem as an optimization problem, and it turns out to be a non-convex problem, and we convexified it based on the engineering principles. So, but sometimes the payload is unknown, such as in the scenario of search and rescue. So the second part of my research is about the payload inertial property estimation, such as the mass, CG location, and the momentum inertial. Because since we have this measurement on the reference point of the payload, by knowing the total force, the payload inertial parameters can be estimated by properly exciting the payload motion. So I came up with a series of excitation motion to make the parameter underestimated observable. So finally, about the trajectory planning. So it is intuitively appealing to operate all these vehicles at near equal energy consumption. So think about if one of the vehicle take the major part of the load, this would lead to an inefficient global performance. Or if one of the vehicle lose effectiveness during the flight, the whole fleet will just break down due to the physical attachment. So I propose a method that simultaneously plans the payload trajectory and the cable force while satisfying the path and force constraints and equalize the cable load. So we've done a lot of experiments to validate the developed system. So the first one is the impulse disturbance rejection. So here, my colleague was there poking this payload multiple times. So you can see even under a fairly large amount of disturbance, the system still can maintain its motion. And this video shows I was there using an Xbox video gamepad to actually flying the payload. I directly sent the velocity and heading command to the payload. Since the payload is the team leader, like I mentioned, it can compute all the rest of the command for the drones. So you can see I can fly the payload as if I fly a normal quad rotor. So the whole fleet can be regarded as one single drone with payload leading. So we then bring everything outdoor under a realistic environment. So here we switch from the motion capture to the RTK GPS to further validate our system performance. So here we validate even under the real environment, it can still achieve a outdoor lateral trajectory tracking. So finally, I put my estimated payload parameter like CG and mass and moment of inertia to compensate the control loop. So here my whole fleet is flying a figure 8 pattern with a faster and faster frequency. So you can see compared to the case without adding the estimated parameter, the system can achieve better performance by adding the estimated payload inertial parameters. So we further showed the system performance under the planning method I proposed based on load distribution. So this curve shows, let's say the red curve showed using my method, the cable tension variance clearly reduced, but without planning based on load distribution, like the blue curve showed, it ended with a very large cable tension variance. So by using our method, the total robot power consumption get reduced, as well as the standard deviation of the robot power consumption also get reduced. So with after this comprehensive cooperative aerial delivery project, I worked on another aerial transportation research using eVTOL. So the hybrid eVTOL takes advantage of both multi-rotor and fixed wing so that it has the VTOL ability during takeoff and landing without the needs of building a runway, and has a high aerodynamic efficiency during the cruise in fixed wing mode. So there are in general 3 types of the eVTOL to balance the configuration complexity and the control simplicity. For example, the tail seater has the minimum amount of actuators, but it's the hard to control. And the fixed rotor eVTOL is the easiest to control, but it adds additional weights from the separate hover and forward flight propulsion system. And as for the tilt rotor, they are easier to control in hover than the tail seaters due to more control authorities, but the additional tilting mechanism increases the system complexity. So we noticed that most of the eVTOL has more actuators than it required. We're thinking, can we leverage this redundancy for safe control? Because it's a very important topic for the aerial vehicle. Here it shows a crash of one Joby vehicle last year. It brings the safety issue again for us to think about this problem. So we built a tilt rotor eVTOL. Our design consists of a quarter rotor frame and a fixed wing frame. It transits to forward flight through tilting 4 rotors, and the direction of the 4 propellers can be individually controlled. So different from some of the existing design, which have the additional arm length over the wing, which may cause the interference of the tilt, our quad rotor arms can entirely separate from the main wing, which makes the control less affected by the unexpected wing deformation. Moreover, the quad rotor arm have airfoil cross sections, which can provide additional lift for the vehicle during the forward motion. So although the PX4 or the PICSOC provides the off-the-shelf controllers for this type of aircraft, it usually needs to load the proper mixer file to map the desired control range to each of the actuator inputs, which can only handle the aircraft with a fixed configuration. Instead, here, we developed a dynamic control location scheme so it can adapt to potential vehicle configuration change, such as the actuator failure. So basically, if some of the actuator fails, the allocation automatically allocate the net force and moment to the rest of the healthy actuators. Here, since the system has redundancy, we still leverage the null space or the non-zero null space to formulate the whole problem as an optimization problem. So we compared the vehicle performance under motor failure in the multi-rotor phase with a case where the controller wasn't informed of the failure or informed there is a failure. So you can see when the system is informed there is a failure, it is able to maintain control flight during the dynamics control location. So without the failure knowledge, the system is still trying to allocate a control range to the failed actuator, result in an immediate aircraft crash in the aggressive rotation, losing control, and finally crash. We also compared the motor failure in the fixed wing phase with the case where the controller wasn't informed there is a motor failure. So you can see without knowledge of the failure, the system cannot maintain the cruise flight as expected, with a significant deviation from the desired path. but when the system is aware there is a failure, it is able to maintain the controlled flight. So our system can also handle several other types of failure, such as the tilt failure, control surfaces, like the aileron failure and elevator failure. So our ultimate goal is to use this eVTOL platform for the delivery tasks. While we were working on the safe control project for the tilt rotor eVTOL, we also developed algorithm to perform delivery tasks on a fixed rotor eVTOL. We used the visual guidance from the apron tag to guide the final delivery without landing. We also designed a releasing mechanism for the delivery. So this video shows the takeoff and transit, and here shows the transit back and the delivery. So we can see even with a box of eggs, we can deliver it without any damage. Yep. So with this, I would like to conclude the first aerial transportation application I was working on and move to the real aerial manipulation. So like I said, the aerial manipulation intends to let the drone really do something. When perform manipulation tasks for the real world, the state estimation is really challenging because the GPS signal is degraded when the drone is near the building. For some featureless environment, it is also not easy to use the SLAM techniques. So the existing techniques mainly focus on the controlled lab environment. The vehicle rely on the motion capture system with some predefined visual markers, and most of the work use very complex mechanical design here to attach a robotic arm directly attached to the under-actuated quad rotor. So we developed a visual servo control to deal with this issue. So basically, in general, there are two methods: position-based, where you use the visual guidance to estimate pose and then fit into the control loop, or the image-based, like us, we did here, to fit the pixel error in the image plane directly into the control loop to bypass the pose estimate. So we proposed an aerial painting strategy to use the drone to paint the bridge. So basically, when the drone is far away from the bridge, we leverage the GPS signal because it's still close to the infrastructure. When it's close to the infrastructure, we switch to the visual servo control because right now the GPS may be in a degraded scenario, and we start tracking the bottom edge of the bridge, and then we switch direction once it detects the vertical edge of the bridge, and then we switch direction to paint the background by tracking the painted line during the first round. So in particular, we leverage a fully actuated hex rotor UAV. So here, if you notice, we rotate each of the rotor here to some degrees, so it can generate the thrust on all directions instead of using a common quad rotor, which has a coupling thing between translation and rotation. So our system architecture is like this. We have a fully actuated UAV, and the onboard camera provides us depth and RGB image, and then sent to our vision module, where our vision module try to do some filtering and line detection to provide us the bottom edge of the bridge. And then it will send to our control module. So here we created a hybrid force and motion control to close the control loop. So in particular, we have a range tracking controller. So here, notice that we leverage a zero tilt strategy to help to let the drone always maintain the level flight by doing this. And our range tracking controller mainly ensure the vehicle hold a constant force to the surface. We do have a force torque sensor at the end of this end effector to guarantee the painting quality. And on our motion controller, it consists of two components. So the visual servo controller mainly correct the vertical motion with image feature error. And the second component is the complementary motion control. It does the horizontal velocity control, leveraging the IMU data. Basically, try to handle the dimension where the visual servo control cannot be handled under the zero tilt strategy. So we also compared our system performance with a impedance control and a pure force control. So here we showed by adding the impedance control to the system, it significantly absorbs a lot of oscillation energy and make the whole system even more stable. And this video shows the final aerial painting performance in the high fidelity gazebo environment. So you can see the drone is always holding a constant force to the wall to guarantee the painting quality and also track the detected line by the camera and do the painting to the end. And this code has been deployed to a real drone. So this video shows a short demo to show the visual servoing performance using a virtual target. So here we just let the drone to go up to a virtual horizontal line while maintaining the constant contact force. Okay. So with this, I conclude the first two parts and from here, I'd like to share some of the experience I had on the general robotic manipulation I did in the past several years. And the first one, which I think is interesting to share, is the use of robot to do the depowdering. The depowdering is actually a process of removing the unused powder surrounding the 3D printed parts. It is an important pro-processing step for the powder-based additive manufacturing. For example, the 3D print parts need to be extracted from the built box with the residue powder removed before sent to the subsequent process, such as the heat treatment and surface finishing. But traditionally, this process is often performed manually, where the human operators use vacuum or shovels or brushes and blowers to remove this powder incrementally. However, this process, you can imagine, is very tedious and time-consuming and costly, and also the raised powder may cause damage to the human respiratory system. So therefore, we're asking, why don't we leverage a robot to do this? So it's actually a challenging task due to various kind of reasons. For instance, the 3D printed parts may appear in a similar color to the background, and features such as edges may not be available due to some occlusion. And in addition, the visible surface gradually change during the depowdering, where the 3D printed parts are not anchored to the building blocks. They might move or lose balance during this process. So we developed a robotic system to automate this depowdering process. And then specifically, we designed a visual perception system for the 6D pose tracking via the ICP algorithm and template matching. So the whole architecture is like this. The input to the system are the CAD model and the scan point cloud. And these two things will be sent to our developed conditionally updated ICP algorithm. Then, based on estimated pose, we generate a powder contour to estimate the progress of this whole process. At the same time, our motion planning system generates a path for the depowdering. Then the vacuum gripper on the robot arm conducts the depowdering process. So this video shows the process of the whole depowdering process. So we have the arm here, and the LiDAR camera, and the printed part in the building box, and it starts depowdering using the vacuum gripper. And based on the point cloud scan and a known CAD model of the parts, we can track the 6D pose of the parts. And based on the detected parts, we can generate a path around it, and then the vacuum gripper can remove the powder. At the same time, we can estimate the progress, and one unique thing is we can do the template update compared to the normal ICP algorithm. The algorithm can handle multiple parts, different shapes, and even can readjust to the parts movement when it's fall. And finally, we use the air blasting for the last amount of residue powder. Yes, So from this video, we can see estimating the 60 pose of the object from the camera images is a very important problem. However, even like the video showed, the majority of the existing work have mainly dealt with the instance level 60 pose estimation, where a set of 3D CAD models of non-instance are given as prior. So this significantly limits the practical robotic application. So in the category level estimation, the estimator is able to handle unseen object and only require training one network per category. So this method will significantly reduce the time and the cost to train a pose estimation module for a new object of a certain category. So we proposed a category level pose and shape estimation pipeline, which use a raw black wall-less particle filter with an autoencoder network for measurement update, and then a pose and size refinement module, and the shape estimation module to estimate the shape. So the whole pipeline can handle unseen object, can track the fall distribution over 60 object poses, and can estimate object shape. So in particular, the key part for the particle filter framework is the measurement update. So how to predict the measurement based on the current observation is the important thing. We propose autoencoder network to be our observation model. It consists of an encoder and decoder network, where it takes into the normalized depth image for an arbitrary object in the same category under arbitrary orientation with domain randomization, and then reconstruct the whole thing from the normalized depth image of a canonical object selected within the same category, under the same orientation as input with no domain randomization. So in this way, the code in the middle will be independent of the code object instance and can handle the intra-class variation. So with this autoencoder network, we can pre-compute a codebook for object under our discretized orientation. The code in the middle will record the feature, how similar the current object orientation is with that stored in the codebook, so that we can use this as our observation prediction. And based on this estimate pose, we further refined the object pose by sending it into a PointNet++ or the latent network to further estimate the shape, combined with the deep SDF decoder network. So this video shows the example of our pipeline applying to the object tracking. So the green object is the rendered object based on the current estimate. We can see it align well with the captured image on the bottom, indicating a good pose estimate. Compared to the state of the art, our tracking performance are much more stable with higher accuracy and can provide temporary information. It will be very useful for the factory to switch production line for different parts, but within the same category. So our pipeline can also estimate the object shape. So thanks to our SDF-based latent representation, so although given some measured partial point cloud, our method is still able to reconstruct the full 3D shapes from the estimated shape latent vector. So with this, I finished all the research sharing. And what's the next? So I'm basically interested in three parts: the aerial manipulation, the new configuration UAV, and the learning control. So like I said, the how to create a precise contact model to guarantee the manipulation performance is a key part. And in real world, how to handle the wind disturbance, the boundary layer, or the ceiling effect are some interesting topic I'm planning to work on. And also when the drone is close to this bridge, the repeated pattern may cause a perception uncertainty plus some other perception uncertainty for the system. And I'm also interested in the new configuration of UAV, like I mentioned. So besides the safe control, so how to involve the control performance design at the design phase or the control code design is the interesting topic. And also how to create a unified control profile instead of separating the multi-rotor phase and fixed wing phase is another interesting topic I'd like to work on. And finally, I'm right now collaborating with some previous colleagues to develop a library for robotic learning with physical-based optimization. We try to combine the learning-based method with model-based method to provide the physical guarantee to make it interpretable, certifiable. So if you Google PyPose, it has already been released. So far, it has the perception, planning, and control. and I'm the lead of the control part. And we've been released the learning-based LQR, MPC, and we're ongoing developing the differentiable PID and MPPI. This work just been accepted in this year's CVPR conferences, and we will present in Canada in June. And with this, I'd like to conclude my talk. Thanks everyone for attending. At the very end, I would like to show a short video. And since I'm the only person working on the multi-lift project, I handled all the algorithm hardware. There was a lot of fun moments. And in the middle, and I'm happy to answer any questions. And as always, I'm looking for more collaborator at this stage. I just joined Penn State for 2 months. Yeah.
Thank you, Junyi, for the presentation and the music. I always enjoy seeing the failures right at the end. So maybe it gives a false expectation, right? That robots, work nicely all the time. So there's a lot of hardship. We thank you everybody for joining. We have time for a question or two. I had a question, and Michael Odie had a question as well regarding the robustness of the controllers and potential wind disturbances, wall effects, or ground effects. I guess you kind of addressed it at the end, saying that this is some of the line of research that you want to approach in the future. Do you have any thoughts on how you would handle the robustness?
Oh, yes. Right now, like I said, I try to combine the learning-based method with the traditional method. We try to fly the drone behind the big fan first to grab some of the flight data. And at the same time, we are working on a learning Koopman operator for the system to make it linear, so that we try to make the model more robust. But at the same time, we will put the learned model in the traditional MPC framework, so it combines both the advantages of the learning method and the traditional method.
Thank you. And so with that, maybe Junyi, will you mind stop sharing so we can share the screen?
Okay. Yep.
For the Michael stop. Just to acknowledge our sponsors one last time. I want to thank everybody who's stuck around here for our seminar series. One up, Michael. So again, if you have any, if you would like to learn more about the opportunities to interact with the Mariner Robotics Center, please visit the link here. Thank you all, and we'll see you during the next Future Leader Seminar Series.